Hello, my name is Kwesi Nkromo, and this summer I worked on the Mudskipper robot as a RIS 2025 scholar. I worked in a Zoom lab while mentored by Professor Zeynep Temel and Shaswat Singh. In this project, I aimed to make a robot that was inspired by the Mudskipper, mostly for its jumping abilities, to use it for either potential search and rescue efforts or just general exploration. To the right here, you can see a picture of the Mudskipper. It's capable of swimming, jumping, and crawling, which makes it a very versatile animal, which is why it was chosen for the base of this project. And to the left, you can see the completed design of the robot, which is details I'll go into later on. The core part of the robot that allows it to actually jump out of the rubber bands because of the ability to store energy inside of them and release it for an explosive response through elasticity. Here I chose to use three different kinds of rubber bands with different thicknesses to test how they interact with the robot based on how high it jumps and how easily it can maintain its balance when jumping. The way energy is stored in the rubber band and released is through rack and pinion technology. Here you can see a detailed look at the robot and its different parts. A gear wheel allows the motor to travel down the rack structure to load energy and release it for a jump. These sliding holes keep the motor in place and to not let it dislodge, while also allowing it to travel up and down the rack. And here you can see it actually in motion. Here is a neutral position, and then it loads energy in the rubber band, where it gets to the smooth section of the wheel, which allows it to then jump. The platform is connected to the rack structure through elevated holes that use friction to keep it secure, while also being able to remove it instead of gluing it together. Here you can see three platforms that are developed in order to observe how they interacted with the robot when it jumps. The flat platform is standard, while the round platform was in theory allowed to return to position easier when it jumps, and the claw platform has less surface contact, which would theoretically make it easier to jump. To gauge how well the robot could jump, a power supply bank was used to give constant voltage to the motor, as well as controlling how fast it would run depending on the amount supplied at a time. A measuring background was used to gauge how high it could jump, depending on the combination of components it possessed. Each of the rubber bands was used in 3 trials per platform to test which combination worked the best overall. Here are a few video examples of jump testing based on the platform being used and the elastic band being used. With a flat platform, the robot is able to jump up consistently as well as breaking away cleanly from the surface. With round platform, the robot shows to be a little more unstable and is not able to jump up quite as high. And with the claw platform, the robot seems to jump the highest, although it cannot break away cleanly from the surface due to its structure compared to the first 2 videos. Here are the results of the trials based on the combination of the different platforms and different rubber bands. For the flat platform, the results are mostly consistent, but the bars being largely the same. The thickest rubber band had the best height due to having a low elasticity, therefore creating a stronger response when it's released. For the round platform, the second thickest rubber band has the best results on average due to having the best compatibility with the robot, being in maintaining balance and in maintaining a decent jump height. And for the claw platform, the thickest rubber band has the best heights. However, all three suffer with constant results because of the increased elevation of the claw platform, making the weight distribution unbalanced. In order for the robot to operate untethered, a microcontroller is used to run the motor and control speed without needing to be connected to a power bank supply. Instead of that, a 3.7 voltage battery acts as a power source for the robot. However, it lacks the amount of current necessary to actually run the motor, so a motor driver is used to increase the current and allow the robot to actually run with the microcontroller and the battery. And here is a short demonstration of the robot jumping using the microcontroller as well as the second thickest rubber band and the flat platform. As you can see, the robot can consistently jump, and although the thickest rubber band will produce a stronger response, I opted to use the second thickest as it was most compatible with the increased weight because of the microcontroller, whereas the thickest rubber band will be too strong and cause the robot to lose its balance and fall over. So after completing the trials, the flat platform, in conjunction with the thickest rubber band, had the most favorable results with a combination of consistent jumping and higher vertical distance compared to the other trials. Unfortunately, the round and claw platforms were not as reliable as the jumping was not as consistent compared to the flat platform. For untethered locomotion, the second thickest rubber band was most compatible with the robot with the increased weight due to the microcontroller. In future work, more testing can be done with the round and claw platforms in different terrains such as mud and dirt to highlight the adaptive element of the robot. And springs will be explored as an alternative method for the elastic component for increased durability and more quantifiable elasticity compared to rubber bands. Thank you to the RIS team for the opportunity to perform research at Carnegie Mellon University for the summer 2025, as well as Kip Braille's Foundation for making the connection possible. Also thanks to Professor Zeynep Temel, Shashwat Singh, and the Zoom Lab for the continuous support and guidance. Thank you for watching.